If you strip modern life down to its physical foundations, semiconductors are near the center of everything. Phones, laptops, cars, internet infrastructure, medical devices, and power systems all rely on them. The reason is not that semiconductors are the best conductors of electricity. In fact, they are intentionally not. They sit between conductors and insulators, and that middle position gives engineers control. A perfect conductor is hard to turn off. A perfect insulator is hard to turn on. But a semiconductor can be tuned so current flows only under specific conditions. That controllability makes logic possible, and logic makes computation possible. In everyday speech, people often use the word semiconductors to mean chips or processors. But at a deeper level, semiconductors are materials with tunable electrical behavior. The device revolution began when humans learned to shape that behavior precisely and repeatably. To see why this matters, compare the three electrical categories. Conductors allow charge to move easily, so they are ideal for wiring and power delivery. Insulators resist charge flow, so they protect circuits and isolate components. Semiconductors are different because their conductivity can be changed by design and by environment. You can alter it through chemical composition, external electric fields, temperature, and light. That means one material can act as a blocker in one state and a pathway in another. This is the foundation of switching and amplification. Switching gives digital systems their ones and zeros. Amplification lets weak signals become useful outputs in communication and sensing. So semiconductors are not just passive materials. They are active platforms for controlling current. Once this was understood, electronics shifted from bulky electromechanical systems to compact, fast, and programmable solid-state systems. Inside a semiconductor crystal, current is carried by electrons and holes. Electrons are familiar, negatively charged particles that move under electric fields. Holes are equally important in semiconductor theory. A hole is effectively the absence of an electron in a state where one could exist, and this absence behaves like a positive carrier. Using both concepts allows engineers to describe transport accurately. In a crystal lattice, carriers do not move through empty space like planets, they move through structured energy environments set by atomic arrangement. Their concentration and mobility determine conductivity. If carrier populations are low, current is limited. If carriers are plentiful and pathways are favorable, current increases. The key is that semiconductor engineering can set these conditions region by region. So device behavior is not accidental. It is the result of carefully managing carrier populations and carrier movement within a precisely fabricated crystal structure. The most important control method is doping, which means introducing tiny amounts of impurity atoms into an otherwise pure semiconductor. In silicon, even an extremely small dopant fraction can dramatically change conductivity. This sensitivity is why fabrication requires strict process control. Different dopants create different electrical effects. Group V dopants such as phosphorus, arsenic, and antimony tend to donate extra electrons, producing N-type material where electrons are majority carriers. Group 3 dopants such as boron, gallium, and indium tend to create acceptor behavior, producing P-type material where holes are majority carriers. Doping does not simply make a material good or bad at conducting. It shapes how the material responds to voltage, fields, and temperature by changing available carriers. Because doping can be spatially patterned, engineers can define functional regions directly inside one crystal. That is the basis of nearly all semiconductor devices. When P-type and N-type regions meet, they form a p-n junction, one of the most useful structures in all electronics. At the interface, electrons and holes diffuse toward each other and recombine. This leaves a depletion region with fewer mobile carriers and creates a built-in electric field from fixed ionized dopants. That field sets up an internal potential barrier. External voltage can then push against or support that barrier. In forward bias, the barrier is reduced and carriers cross more easily, so current rises strongly. In reverse bias, the barrier is reinforced and current is greatly limited. This directional behavior is rectification, and it is why a PN junction functions as a diode. Diodes are used everywhere, converting AC to DC, protecting circuits from reverse polarity, shaping signals, and enabling countless control functions. The PN junction is simple in concept but foundational in impact. The transistor builds on junction and field concepts to create controlled current flow. Its core function is leverage. A small input signal can control a larger output current. In digital electronics, that means transistors become switches that represent logical states. In analog electronics, it means gain, allowing tiny signals from antennas, sensors, or microphones to be amplified. What changed history was not only transistor function but transistor scalability. Semiconductor manufacturing allowed transistors to become tiny, fast, and cheap enough to place in huge numbers on one substrate. This led to integrated circuits, where logic, memory, timing, and interface blocks coexist on a single chip. Instead of wiring separate components by hand, engineers could design systems in lithographic patterns and produce them at volume. The result was exponential growth in computing capability, smaller devices, lower energy per operation, and entirely new industries built on programmable electronics. Silicon became the dominant semiconductor because it offered a strong balance across physics, manufacturing, and economics. It is abundant, relatively stable, and supported by decades of process development. Entire tool chains, fabrication methods, and design ecosystems were optimized around it. But silicon is not universally best in every metric. Gallium arsenide, for example, became important in areas like laser diodes, microwave frequency integrated circuits, and certain solar cell applications where its material properties offer advantages. Material selection in semiconductor engineering is always contextual. You choose based on required frequency, power handling, thermal constraints, optical interaction, fabrication maturity, and cost targets. A material with superior performance in one application may be impractical in another if manufacturing complexity is high. So the winner in real markets is often the material with the best system-level trade-off, not the one with the single highest theoretical parameter. Temperature behavior in semiconductors is another crucial concept. In many metals, conductivity decreases with rising temperature because lattice vibrations increase scattering. In semiconductors, increasing temperature can increase conductivity by generating additional carriers. That opposite trend affects real product design. Engineers must manage thermal conditions carefully because device characteristics shift with temperature. In precision circuits, these shifts can alter timing, gain, and leakage. In power devices, temperature can influence efficiency and reliability margins. Semiconductor response to light is equally important. Photons can excite carriers, changing conductivity, which enables photodetectors and imaging sensors. Related physics drives photovoltaic conversion in solar cells, where absorbed light generates charge carriers that can be extracted as electrical power. These sensitivities show that semiconductors are not just logic materials. They are transduction materials, converting environmental inputs like heat and light into controlled electrical behavior. A full explanation of semiconductor behavior requires quantum physics. Classical models help with circuit intuition, but they cannot fully account for why certain materials have tunable conductivity or why specific dopants create predictable electrical outcomes. In crystal lattices, electrons occupy allowed energy states, and transport depends on how these states are populated and how easily carriers move between them. Doping modifies this landscape by introducing donor or acceptor behavior, effectively changing carrier concentrations and equilibrium conditions. Junctions introduce internal fields and potential profiles that govern diffusion and drift. Device operation emerges from these microscopic rules. Engineers use practical design models, but those models are rooted in quantum-informed material science. This is why semiconductor progress depends on both theory and fabrication. Better understanding enables better structures, and better process control turns those structures into mass-produced devices with reliable and repeatable performance. Historically, semiconductor technology advanced from scattered observations to engineered systems. In the late 19th and early 20th centuries, researchers noticed unusual conduction effects in certain materials but lacked a complete framework. A key early application arrived in 1904 with the cat's whisker detector, a primitive semiconductor diode used in radio receivers. It demonstrated one-way current behavior before modern solid-state engineering existed. As quantum understanding improved, semiconductor behavior became more predictable. That opened the door to the transistor in 1947, which replaced many vacuum tube rolls with smaller, cooler, and more durable switching elements. Then the integrated circuit, demonstrated in 1958, brought multiple components into one semiconductor platform. This integration changed manufacturing economics and system architecture at once. Electronics became smaller, faster, and more accessible, enabling personal computing, digital communications, and automation at scales earlier generations could not realistically build. Today, semiconductors are best understood as a stack of capabilities, not a single invention. At the material layer, controlled doping and crystal quality define carrier behavior. At the device layer, junctions and fields create diodes, transistors, and specialized optoelectronic structures. At the circuit layer, those devices combine into processors, memory, power management, and communication blocks. At the system layer, chips become phones, vehicles, industrial controls, cloud servers, and energy infrastructure. This layered view explains why semiconductors matter so deeply. They connect fundamental physics to everyday function through manufacturable design. The same core principles that govern a simple diode also support advanced computing architectures. That continuity is remarkable. A material class with adjustable conductivity became a universal platform for switching, sensing, conversion, and computation. In practical terms, semiconductors are how modern civilization turns electricity into intelligence and control. If you found this helpful, please like this video and subscribe for more explainers.